Hello, this is integration packet number 19, problem number 4. We're asked to look at the region R, which is bounded by the curve y equals x squared, the line y equals x plus 6, and the coordinate axes. I've actually created this problem in two different ways. And the yellow description I have given actually takes into account the y-axis, and it takes in the coordinate axis of by intersecting through the point 0, 0, okay, which 0, 0 incorporates both the x and y axis. It could also be the green area, which clearly incorporates the x-axis, and with the intersection point still being at 0, 0, it's going to account for both the x and y coordinate axes. So the area problem's not exactly clear as to which area we want calculated, but I'm going to look at the yellow area. So the first thing I needed to do was I needed to find the intersection points, which in order to find that, I just set the two curves to next to one another. X squared equals x plus 6. You need to do a little factoring there, and you're going to find out they intersect at when x is negative 2 and x is 3. So looking at part A, we're trying to find the volume of solid whose base is R and whose cross sections cut perpendicular to the x-axis. Perpendicular to the x-axis is equivalent to parallel to the y-axis, right? So now you have to think about these rectangles that I'm about to draw as effectively going, the base being what I just drew in blue, and then a rectangle coming out of the video towards you. Now I'm trying to draw a three-dimensional object on a two-dimensional screen, which you know that I'm not much of an artist, so I'm going to do the best that I can. So we have this rectangle coming out towards you, if you will. Now I drew I don't particularly like how I drew it, so I'm going to do a little bit of editing on there. Now, if you notice, the rectangle I have made longer as it comes out towards you than what it does on the base between the two curves. And the reason why I did that was the height of the rectangle is supposed to be twice its length. And its length is defined by its base is defined between the two curves. So we're going to have a series of these rectangles, all right? And they're all going to be of different lengths. One just a little bit shorter or a little bit longer than the next one. Okay, so we have them coming out. Eventually, the largest one will be right on the y-axis, because that's the farthest point where the two curves separate from one another. Okay, so we're going to have a object that kind of has a shape that ultimately has a rectangular end to it, and if you cut through as though you're cutting a slice of bread, as you cut through, each one of those slices would be a rectangle. Okay, so hopefully my diagram helps you a little bit anyway. So in order to find out what the volume of this object would be, in order to get volume, you need to add up all the cross sections. In our case, the rectangular cross sections. They could be any form whatsoever. They could be, the next one we're to do are semicircles. You could have right triangles. It could be anything. Main idea is that you are adding up whatever the area of that cross section is. So the area of a rectangle in general is the base times the height, or the length times the width. And in order to add them all up, I have to go from where my intersection points are, and those are x values because my widths are dx's. That's a dx width in there. Okay, so my x numbers intersection go from 0 to 3, and the integral, I need to multiply my base times my height. So my base is the distance between the two functions. So I have the area of the two functions, or the base, is going to be this length right in here. So I'm going to take my higher curve minus my lower curve. My higher curve is the line, which is x plus 6, minus my lower curve, which is x squared. So that's my base. I need to multiply that by my height. And they tell me my height is twice the length of my base. So the height is 2 times my base and of course I need to recognize that I have dx widths. Okay, so I'll let you go ahead and solve that. I would suggest that you multiply it all out and then do each one as a individual polynomial integration. Part B of the problem asks us to, again, find the volume of a solid whose bases are and whose cross sections now are cut perpendicularly, so we're looking at the same way to cut them. We're going to have a dx width, all right, and so the base is on R and whose cross sections cut perpendicular to the x-axis are semicircle. So on each one of these different widths, different diameters, I'm going to have a circle or a semicircle sitting up there. Okay, so again, each one's going to be a different size, and the largest one being where it intersects with the y-axis. Okay, so I'm trying to find that volume. Well, the area, to find volume one more time, we need to add up area of the cross sections. Now I know some people have trouble visualizing these objects, and if you are one of those, then all I suggest is that you recognize what it is, what figure, and in our case now, semicircle, what figure do you have to add up? And then determine what's the area in general of a semicircle. Well, the area of a circle is pi r squared. The area of a semicircle is 1/2 pi r squared. So I know this point goes to 3 out here. So I'm going to set up my integral. I'm going to go from 0 to 3 again. If I have a semicircle, I have the half of pi is a constant, so I can pull that out. And I need my radius squared. All right, well, my radius is not just the difference between the two curves, the line and the parabola, but my radius is half of that distance. So how do I recognize my radius? My radius squared, it's going to be half of the x squared. Oops, sorry. It's the line is the higher one. So x plus 6 minus x squared. And I have to have my radius squared, so that whole term is squared dx. Now, I have that a little bit off, so I need to square my radius. This would be, as I have it right now, what I'm doing is I'm actually squaring, as it is now, I'm squaring the diameter. So I need to change that a bit. It really should be from pi over 2, from the integral 0 to 3 of the 1/2 x plus 6 minus x squared, this whole thing squared. So what I was doing was I was missing squaring this half where I had my parentheses. So you and I both need to be careful about that. The only thing that I'm going to say is, further I'm going to let you do the rest of the calculations here. But this 1/2 is squared. 1/2 squared is 1/4. I can take that 1/4 out of the integral, and I could have it as pi over 8, the integral of 0 to 3 of x plus 6 minus x squared dx. You will have to multiply this term in here out in order to square it. There is not a u that will work for u substitution. It's just one of those algebraic ones that it's not set up perfectly that the integral would happen. Or you can plug it into your calculator and let it take care of it. On the AP exam, you may get it either on a calculator section or a non-calculator section. Part C of the problem asks us to find the volume of the solid generated by rotating r around the line y equals -1. So I've set up a little diagram. I've added in 9 into the visual of the graph. It's x squared, put in 3, you get 9. We're asked to rotate this around the line y equals -1. So if I'm going to rotate the point 0, 0, and I'm going to reflect it over -1, that's going to be at -2. And if I have the point 3, 9, if I'm going to reflect that over y equals -1, well, this distance in here is a distance of 10. So I have to go from -1, a distance of 10. So my bottom point, my lowest point, would be at -11. Now, you don't necessarily need to get into that level of detail. I am just doing it to help you. All right. So this point up here is 6. So again, that's a distance of 7 in here. So we'd have to go from -1 to -8. And so it looks something like that. Okay. Now, I am rotating this curve, this region around the y equals -1. So as I rotate, the part that I have going on here is actually hollow. All this inside point is hollow. Okay. The portion that got rotated that actually has area, and as it rotates, this is the part that has volume. So one of my previous, I'm sure during class and on one of my previous videos, I talked about the cross sections of these being called washers. Okay, so if you take and you slice right through this object that's theoretically coming out towards you, as well as inside the video or into the computer that you're looking on this, the cross section is a circle. It's concentric circles, okay, where the longer radius goes from -1 up to the line. Okay, and then the shorter radius goes from -1 up to the x squared. Okay, so when I have washers, I can set up my integral as the big washer, the outer one, minus the inner one. Okay, or the higher curve minus the lower curve, each of those areas. So if I do the outer curve, okay, its area, to get its volume, I have to add up area. So I'm going to go from 0 to 3. The cross sections are still a dx. 0 to 3. I have pi. I have my radius squared. In this case, I'm going to the line. So x plus 6 minus, just x plus 6, sorry. Because the radius goes the whole way down to the, sugar, that's not right. So I just erased that. So the whole radius goes from the -1 line up to the line, okay? So I have to take care of that whole radius. So that would be the line minus the line x plus 6 minus the line y equals -1. So that's the blue circles, the larger ones, okay? And of course I have to have my dx. Then I'm going to subtract off my inner circles. So these green circles I'll put in here that go from, the radius goes from -1 up to the x squared. Okay, so this is the hollow part. All right, so I have to subtract off that area because it's empty. Okay, so to go from the parabola minus the line y equals -1 dx. Of course, you can do some quick algebra, quick subtraction, okay, and make that x plus 7. And x squared plus 1 dx. And then to maybe or maybe not, depending on how you feel about it, you can solve it from there, or as I've indicated in other videos, I can consolidate it down to one integral, because they both have pi, they're both going to the same limits. So, so I can have the pi outside, and then I'd have the x plus 7 minus the x squared plus 1 all dx. And you know that I like to have the final set of brackets or parentheses around them. So in that case, I'll get a little bit further for you and let you handle the rest. So that's a negative x squared, positive x, plus 6 dx, and you can take it from there.